One of the nice things about the LIQUiD simulator is the ability to simulate some fairly complex circuitry on a classical machine. Now, this is something that in general is very hard. The naive numbers scale very poorly, that if I had 32 qubits, I need 2 to the 32nd locations in memory to store the state. I need an input state, an output state, and then I need a matrix that's 2 to the 32nd by 2 to the 32nd to actually operate on the state. We can do much better than that. And LIQUiD is really good at optimizing for the classical machine. We're able to do things you can't do on a quantum computer because we're classical. So we take advantage of that as we're running simulations. So if you naively first write your circuit and run it on the system without doing anything, you will get exactly how the quantum computer would operate on it. But since this is linear algebra, we can take many tricks that you could use in linear algebra to speed up the classical machine. In one example, we can just take every circuit and take these gates that talk to 1 or 2 qubits and combine them together into bigger and bigger matrices. A single matrix operation, instead of doing hundreds of them, can be much more efficient on the classical machine. And LIQUiD knows how to trade these off. We can get many orders of magnitude speed up in the simulation of a quantum system by optimizing the linear algebra. This is one of the main things that happens when you call the grow gates routine that's in the API and is also documented, and an example is shown in the tutorial that is available on video on this website. So walking through that will show you how to write a simple algorithm, play with the algorithm, and then optimize it to make it run a little faster. This is also how we run Shor's algorithm so much faster. If you take the final argument and change it from a false to a true, the true says optimize the circuit. And when you optimize the circuit, you'll find it runs 2 to 3 orders of magnitude faster on the bigger factoring problems. There's a second version, also part of Grow Gates, that understands physical simulation. So if we're doing quantum chemistry or quantum materials, we can take advantage of things we know about the problem, not just the linear algebra. For example, every time we apply a gate, the number of electrons don't change in the chemical. Therefore, we can take advantage of that and only keep the lines, or if you will, the lines of the matrix or the pieces of the state that have that number of electrons. We also know that while we're sitting there, the number of electrons that are spin up and the number of spin down don't change. So we can get rid of every place where they would change. This winds up compressing problems in quantum chemistry down to very small sizes. So for example, when you solve water, which is built into the samples, H2O would normally take 32,000 by 32,000 matrix to describe the operation. When you do all of these compressions, the system becomes 441 by 441. It's a tiny matrix. We can now work on that entire problem as one matrix. We can exponentiate it, we can solve it, and these optimizations all make LIQUiD run extremely fast compared to a naive direct implementation.